today, this Wednesday after Labor Day. I've returned the tests. The average uncurved was something like 78. So really not too bad for the first test. If you didn't do as good as you hoped, just strive to do better next time. I'm trying to keep it somewhat similar to the homework. Hopefully you found that. If you did good, don't get too cocky. I've had a couple people that suddenly do very good on the first test and then suddenly like let it slack too much and then suddenly get surprised on test 2. But I gave additional 7-point curve to everyone. And that's reflected on your Google Classroom score. The lab today will be the property of light lab, which will be hopefully a fun lab and more importantly, a short lab that will be playing around with prismatic glasses and emissions of light from burning metals and then looking at absorption spectra. But for the pre-lab, there's like 4 or 5 questions. Just a quick overview. Question number 2 and question number 3 are pretty straightforward. You turn wavelength into frequency into energy. You have to make sure to convert nanometers to meters in order to do that. I'm going to quickly go over question 1 and the last question real quick, just for the sake if you haven't already figured those out. Question 1 is actually rather easy once you realize what they're asking. They want you to turn frequency into frequency into wavelength. So you're going backwards, but they give you 126 hertz frequency. Well, hertz is equal to a per second. So really what they're telling you is you have a frequency of 126 inverse seconds. So all you have to do is say, instead of c divided by lambda, you have to say c divided by nu will give you your wavelength. Now, because c is the speed of light in meters per second, that gives you the wavelength in meters. Finally, because they ask you what is the wavelength in nanometers, then you have to convert whatever that number is into nanometers. You have to convert per seconds into nanometers. So that is question number 1. Question number 2 uses an equation that, if you look in the lab report at the beginning, it'll talk about Beer's law. Beer's law is essentially a law of absorption that says absorption is a function of the molar absorptivity or extinction coefficient or something like that, depending on what it's like absorbance equals ABC or something like that. But that it's dependent on how the compound absorbs times how much surface area does it have to pass through, what volume of space does it have to the light have to pass through, times how much atoms are in there, which is the concentration. We haven't quite learned what concentration is yet, but it's like a molar density. How many moles in a liter? But they give you, that's 0.325. They say the absorbance of a sample of 0.325 passing through a wavelength, a path length of 1 centimeter. They give you the absorbance, they give you the path length as 1, and they give you the concentration as 0.325. All you have to do is find what is your molar absorptivity E. I realize there's a giant glare. There. I'm guessing that's from the sun, but so you have absorbance on one side of the equal sign. You have 1 times 0.325 on the other side. So all we have to do is solve for your epsilon, your molar extinction coefficient. I'm not going to take it any further because hopefully you know how to you can do this. If you can't do this, that's a test that'll show me I need to work with you a little bit more. So do let me know. It's like, oh, I have no clue what that is or how to do that. And I will try to take some time my schedule to help you. But that is the last equation. And it basically says, like, well, the more atoms it has to hit, the more space it has to go through, the better a sample absorbs, the more absorbance we're going to read. Okay. Okay. So we just finished off going over light, the last class. We went over the first 4 or 5 slides that talked about how light has a wavelength and a frequency. So what we have here is now we're going to relate this back to chemistry. We're going to relate this back to atoms. This is going to be a little complicated. I'm going to try to take it as we can take it, but we want to relate this back to the atom, because when we talked about Rutherford's gold foil experiment, what did he find? He found that there's a nucleus that's positively charged. It's very dense. It's in the center. There's an electron cloud that's mostly empty space in the atom that the particles pass through mostly without hitting anything. But when it hit the center, it bounced back. But we don't really know how this really looks like. They predicted, okay, maybe it's like an orbit, like a planet. But we don't know much more beyond that. We always see when we draw an atom, we always see something like, oh, here's a proton, a neutron, and then we have whatever. That's how we like picture atoms and like in science. No, it's not very. Trying to think. That's not showing up too well, is that? Let's see if this one's any better. Maybe. God damn this board. Okay. But it's just basically that we show like the atom with the electrons orbiting around it. But we don't really explain it beyond that. Well, eventually we're going to get into a field called quantum chemistry, which is where essentially a bunch of physicists took a crack at chemistry and tried to explain the nature of the atom and tried to explain how the electron cloud is going to work, how the atom is actually made up. And in fact, there's whole fields of physics that go on breaking down what is an atom what is a proton made up of, and you a bunch of quarks and all that, and what is a neutron? Well, it's a bunch of different quarks. So they can go further still, but we're not going to bother with that. So Niels Bohr proposes a model of how this is going to work, that essentially the electron will orbit the nucleus at a specific distance, and each distance will have a discrete energy level. So if we can imagine this like a planetary orbit, at least to start off. Like we know Mercury has an orbit around the sun. It's so close. We have Venus. We have orbit around the sun further away. We have us, the third planet. It's even further away. Each of those orbits would be like an energy level. And in terms of electrons, electrons can actually jump between these orbits. They can jump between these energy levels. The lowest energy level that is available is called the ground state. But any further energy level will be at higher energies and thus will be excited states. So when light is absorbed, electron can be excited to a higher energy level. It would be like if I put rockets on Mercury and pushed it away from the sun. I took a bunch of energy and pushed it into Venus's orbit. It could be done. It takes a lot of energy. The electrons, you take a lot of energy to move it away from the positive nucleus. Now they can relax back down to the previous orbit. When it does, it's going to emit energy equal to the difference between those things. And that's going to result in the emission and the absorption spectra. Last week, we looked at the line spectra or emission spectra of various atoms. And each atom had certain lines that it produced. That is from the emissions of various wavelengths of light coming from jumping between various levels. Now, this equation, nifty as it may be, we will not use it on a test. We will probably not even use it on the homework, but it is a nifty equation, the Rydberg equation. There's a way to model a hydrogen atom and the energy of those line spectrums based on this equation created by like a Swedish school teacher. He was able to model and measure where these lines should come out. He essentially says the inverse of the wavelength is equal to a constant for hydrogen times 1 over n to the first squared minus 1 over n to the second squared, where n to the first and n to the second are just integers relating to the energy levels. So for example, ground state would be that constant times 1 over 1 squared, which is 1, minus 1 over 2 squared, which is 1/4. So 3/4 times that constant gives you 1 over the wavelength of what that light is. Now, if I jump from the first level to the third level, you could have 1 over 1 squared, which is 1, minus 1 over 3 squared, which is 1/9. So 8/9 times that constant would give us that frequency, that wavelength. And if we jumped from 2 to 3, you could do 1 over 2 squared minus 1 over 3 squared. And basically, those 3 to 4 wavelengths that we saw for hydrogen is brought by jumping between these like several energy levels. Why is this not really taught? Why is this not really utilized? It's basically that we can predict energy level for one electron really easily, but electrons have this magical like interference with each other that makes things almost impossible to predict once you add a second electron. And so we're not even going to bother to try to model this for helium or lithium. In fact, there's some really complicated equations that quantum chemists learn that pretty much can only work for hydrogen or hydrogen-like atoms. You would have to do a helium +1 atom or lithium +2 atom, things that don't really exist in real life, don't really exist normally, because there's a certain electron-electron interaction we can't account for. But so there's just idea, there is math, there is method to the madness of where all those lines come in. It's because we have certain energy orbits that electrons are jumping between. Now, so we're going to get to the quantum model. We're going to talk about how do we actually understand these electrons. Well, we previously discussed the massive idea that light can act as a wave and it can also act as a particle, depending on what situations it is. It can be this fluid wave that's always moving, but we can also look at it as a discrete energy, a discrete thing that's going to hit and stop and not continue. Like a beam of light versus a wave of light. Well, a French scientist by the name of Louis de Broglie proposed that, well, if light can act as a wave and a particle, can matter act as a wave and a particle? And that we know matter can act as a particle because it's solid, it's discrete, it's right here in front of us. We can deal with that. But can it act as a wave as well? And in fact, yes, it can. And before you're like, how come I can't see that? Well, it only happens on a microscopic level, on a really nanoscalar level, that we cannot see this because we're looking at on the electronic level in order to see this happen. But electron has a wavelength based on its mass and its velocity. The mass doesn't change, but the velocity can. So we're looking at the momentum of the electron. there was actually a thing in a question that we always must ask when we're measuring things with electron microscopes, because how a regular microscope looks at things by shooting light at it to see it. Well, when we get into the electronic level, we have to shoot electrons at things and then use that wavelength of the electrons to actually bring these into focus. But the question is, how can we know what we're truly seeing is real when we're shooting electrons at it, which could affect it? The idea that by measuring it with electrons, aren't we potentially changing what we're seeing? But that's where we get into Werner Heisenberg, that presented in his uncertainty principle. That basically the idea is, because the electron is moving around the atom and has this variable wavelength, that it has a certain uncertainty in both its position and its momentum, the particle quality and the wave quality. That the uncertainty combined, the more we know one, the less we know the other. Being that if we were to take a snapshot of the atom and found exactly where that electron was, we wouldn't know anything about how fast it was moving. But if we got a good grip on how fast it was moving, it could be anywhere in the atom, including well outside of the atom. The uncertainty of where it's located could be like several meters away. So we cannot know one very accurately without knowing the other. And you've probably seen, well, if you're any nerdy like me, you've probably seen some jokes about Heisenberg gets pulled over by a cop with a radar detector. The cop goes, do you know how fast you're going? And Heisenberg goes, no, but I know exactly where I'm at. And then the cop goes, well, you know, you're going 50 and a 35. And he's like, great, now I'm lost. Thanks. Yes, bad, I know. But okay. So we get into then a bunch of quantum physicists, including Erwin Schrödinger, who develops various mathematical and wave equations that we won't bother to learn. If you go into quantum chemistry, yeah, you might learn some of these, but we're not going to worry about it. But essentially, he describes how you can predict where the electron's at. We can't know definitively where the electron's at, but we can use probability to kind of get a feel for it. If we took a million little snapshots of atom where the electron's at, essentially what you get is a picture like this. If we like time-lapse photography the snapshots together, you'd get something like this, where each of these dots is where the electron is at any given time. The higher density is they are more often than not. And some of these further out regions, less likely to be here. And when we put all these together, we get this orbital, this three-dimensional region of discrete energy level where we can say the electron is most probably located. This is where this electron is located in this electron cloud. In this hydrogen atom, the electron is found somewhere on the surface of this 3D sphere. So it's located somewhere on this sphere, with the nucleus being in the center of this sphere, like an empty bouncy ball. Hollow bouncy ball where the center is our nucleus. And the surface is our electron cloud, where the electron's at. And it's not going to be past this cloud. It's not going to be really in this cloud. It's going to be stuck. Now, we're going to learn about how to describe electrons, and we're going to do it various different ways. And we're going to eventually relate this back to the periodic table. So take this slowly. We're going to try to get this. But the first thing we got to do is understand the basic orbitals, how the orbitals and energy levels will relate. So the first thing we're going to describe is the principal energy level, or shell. Now, when we look at these shells, you can think of this like a Russian nesting doll, that each shell is inside the previous shell, and it's a little bit smaller, a little bit smaller, and a little bit smaller. But as we move out on these shells, we're getting higher and higher energy, but a smaller and smaller difference between the energy levels. So energy level 1, it's the ground state. We can't get any lower energy than this. When we jump to energy level 2, we have to absorb this much energy to get here. Okay. Then we jump to energy level 3, we absorb a little bit more. Jump to energy level 4, a little bit more. 5, 6. Eventually, you could calculate how much energy does it take. There's an asymptote at which point the energy levels don't really change at all. And that asymptote has to deal with that work function of how much energy does an electron have to absorb to be shot out of the atom. When we talked about that photoelectric effect, the work function is how much energy does it take to completely remove the electron from the atom. But okay. So we got here, these energy levels are going to be related to the row. Hydrogen in row 1 will be, the ground state will be in energy level 1. In row 2, lithium, beryllium, boron, carbon, nitrogen, the principal energy level of the ground state will be in N equals 2. As we go into row 3, we're going to be we have energy level 1, 2, and 3. Row 4, we'll have 1, 2, 3, and 4, and so on. There's, 7 rows of the periodic table. So we'll typically only look at the first 7 levels, if even that, and we rarely will go past 6, because 7 is, we get into some really, really weird elements at that point. Actually, 1, 2, 3. Yeah, 7. Okay. But so this energy level N describes typically how big is this shell and how close it is to the nucleus. As we go up and as N increases, the size increases, as does the energy level. Now we're going to break these shells into a variety of subshells, which is actually going to describe what these orbits look like. For this sake, we're just drawing this as a round circle, but that's not actually where the electron's located. It's not just this round circle. It's going to be in these various subshells. So these subshells will have a variety of shapes and a variety of letter designations, S, P, D, and F. These subshells will have 3-dimensional shapes, and that's going to be where the electron's actually located along. And so we'll look at these, and S, P, and D are going to be the most commonly ones we'll use, but mostly S and P is where most of the chemistry will occur, at least for us. Now S, you'll notice there's only one S. It's a single-lobed sphere, so it just looks like a sphere. There's only one S. There's only one dimensionality because a sphere is identical in every way. You can turn it as much as you want, and it's still going to be round and sphere-like. You can't tell whether you're looking at it from the front, back, the left or right, top or bottom. So there's only one for S. And as we'll see, we'll deal with S in a bit. But S can hold 2 electrons. Now P, there are 3 different P orbitals. P orbitals are double-lobed, meaning that you can see 2 distinct shapes there. They look kind of like a figure 8 on its side, or a bow tie, or a dumbbell, whatever you want to picture it. But this P orbital is double-lobed. There's 3 of them. Now, if S was one-dimensional kind of thing, P, or zero-dimensional, P is kind of one-dimensional. That we have a P in the x-axis. Now we can draw a P in the y-axis and a P in the z-axis. that we have 3 different ones because we have 3 different axes. And each p orbital can hold 2 electrons. So with 3p together, we'll see 6 electrons capable of being held total in all of these p's. We get to d's. D's get even more complicated. D's typically have 4 lobes. We go on 1 lobe, 2 lobes, 4 lobes. There's 5 distinct D's. These are going in 2 dimensions. We have a XY, we have a XZ, we have a YZ. We have an X squared minus Y squared, and we have a Z squared. These kind of look like clover leaves. And this weird one, the Z squared, which is like a wheel with an axle. But there's 5 different ones. Each guy can hold 2 electrons. So each one, so D in total can hold 10 electrons. And F gets even trickier. If we've gone from 4 lobes, we've now gone to 6. And it's going all 3 dimensions at the same time. With 6 lobes, they look kind of like flowers. And we have, like 7 different possibilities. So they could hold a total of 14 electrons. We typically will not see F. D is hard enough. I won't expect you to know the XY or the X, the PX, PY. Just recognize there's 3 p orbitals, there's 5 D, 7 F. We probably won't even see F that much. But it's good to know. Now, what happens here? As the principal energy level increases, so as the rho goes up, more subshells become possible. So rho 1 only has 1 subshell, S. Rho 2, because it has 2 rows, has 2 subshells possible, S and P. Rho 3, being the 3rd row, can hold S, P, and D. And row 4, 4th row, could hold S, P, D, and F. And as we go up, the S has lower energy than the P. The P has lower energy than the D. The D has lower energy than F for a given row. So we can look at it like this, but as we actually differentiate S and P, you see S and P. S is lower energy, P is higher energy. Then we see S, P, and D. Then you have S, P, and then you'd have D way up here and F way up there. You'll actually notice something really weird, and we'll talk about this in the periodic table in a minute. The 3D actually comes at a higher energy than the 4S. The 3D actually comes at a higher energy than the 4S. So we'll see this, why something weird happens in a few minutes when we actually talk about this in terms of the periodic table. So one thing we will do is we will look at energy level diagrams. It's going to be really hard to draw these on the test. I might insert a picture and ask you to answer questions about the picture. But we will fill these guys with electrons, with up and down electrons, and understand the atoms. We will also look at the electron configuration of these guys. So for nitrogen has 7 electrons. If I'm doing this, I'm going to have, since I can't redraw, I could draw this on the screen, but it's going to be a pain in the butt. So 7 electrons for nitrogen, 1 up, 1 down. So that's 2 electrons. Up, down, that's 4. Up, 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 that's 7. All 7 electrons are accounted for. If I try to use electron configuration, I say this is the 1s orbital. So 1s, and there's 2 electrons, so I use the superscript 2. So 1s2. Then I go to the next one. 2s, there's 2 electrons, 2s2. Then I go to the last one, 2p, there's 3 electrons in there, 2p3. And we'll see this in a minute, the electron configuration, because I'll actually do some of these where that's not already worked out. Chlorine, 17 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17. All 17. So 1s2, 2s2, 3p6, 4s2, 2p6, 3s2, 3p5. You notice that I could have just started from nitrogen and worked my way over, and that's going to be some of the beauty. If you can find a starting point halfway there, you can build off of that. So start from nitrogen, that's 7 electrons, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Cobalt, getting even harder. That is, God, what is that? 17, 18, 19, 20. 27 electrons, if I'm not mistaken. So starting from 17, 18, finishes off that row. 19, 20, 21, 22, 23, 24, 25, 26, 27. So I'm just adding electrons from my chlorine, adding another 10 electrons. Goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. You'll notice nitrogen and chlorine are in the same region of the periodic table. They both ended up in the P's. Cobalt is a transition metal. It started dealing with the D's. So we'll see some weird stuff going on. But before we go any further, this is how we actually fill in the tables. So how are they actually arranged? We're going to fill these in from the ground state up. So the lowest energy level up based on the following 3 rules. You don't need to, this might be on the homework, but you probably won't need this for the test as long as you know how to use the rules. The Aufbau principle, which is German for building up. The electrons are put into the atom from the lowest energy to the highest. So it's like sand, using colored sand to make a beautiful design in a jar. The sand you pour in first is going to go to the bottom before you fill its way up. So we're going to drop electrons in. It's going to fill up the bottom orbitals before we move up. Hund's rule, that we're going to, all the orbitals in this subshell will be filled prior to pairing them. So when I said the orbitals are degenerate, they are same energy, all 3 of the p orbitals have the same energy. So I'm going to put 1 into px, 1 into the py, 1 into the pz before I start putting electrons together. That is because, remember, electrons are negative. 2 negatives want to repel each other away. So we're going to want to keep them as far away as we can until we have to stick them together. Finally, the Pauli exclusion principle. Each orbital can only hold 2 electrons, and they must be opposite spin in order to be paired. So there can't be 2 up. There has to always be 1 up and 1 down. And the reason behind here is called the right-hand rule from physics. It's basically the idea, if you have an electrical current spinning in a direction, the current field that it generates points in the direction perpendicular to the spin by the right hand. So if I have an electron spinning counterclockwise, I'm curling my fingers counterclockwise, the field points up. If I have a clockwise spin, the field points down. So by making electrons spin in opposite directions, I can get a weak but noticeable attraction between 2 negative electrons. So an up and down spinning electrons have an attractive field that allows them to be near each other. And that's why we can pair two negative electrons. It still is high energy. It's still something that is not desired, which is why Hund's rule takes precedence. We'd rather fill up all the energy levels rather than pair electrons. But that is why we can pair them. So the best thing we can do is just practice. So silicon. I'm going to have to do this on the board. So bear with me. I'll redraw these. But the general gist of this is that silicon, 14 electrons. 1s, 2s, 2p, 3s, 3p, let's see, 4s, running out of room, 3d, I hope I don't have to go any further. Okay, 1, 2, 3. But I'm going to use the same one for each one. Okay, so 14 electrons. I won't have to use all of these for S, but I might have to use it for bromine. But silicon, ground up. 1s, 2, that's 2 electrons. 2s, 2, that's 4 electrons. Like nitrogen, 5, 6, 7, 8, 9, 10 electrons. So 2p6, 3s2, that is 12. So we have 2 electrons left. 13, 14, 3p2. The electron configuration for silicon is 1s2, 2s2, 2p6, 3s2, 3p2. We can build on that for the further examples. Now, the beauty of this, calcium, 20 electrons. I can continue off my previous one because this will all be the same. 2, 4, 10, 12, 14, 15, 16, 17, 18. Then up here, 1, 2 to make that 20. So calcium has 20 electrons, is filled in the 4s. So this becomes 1s2, 2s2, 2p6, 3s2. This is changed to 3p6, and I have to add 4s2. 4s2. Finally, bromine. Bromine, that adds another 15 electrons onto this. I have to have a P up there. Oh, I hope you guys can read this, but if not, I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 puts us at 30. And then the last 5, 1, 2, 3, 4, 5, 35. So with bromine, it's so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. I'm going to briefly ask you to recall chlorine from the last slide. Chlorine was 1s2, 2s2, 2p6, 3s2, 3p5. Chlorine was 3p5. Bromine is 4p5. If I looked at Fluorine would be 2p5. These guys above each other in the periodic table have a similar electron configuration, except for a different row, which is why in the next chapter, when we talk about periodic trends, this is why everything in the same column will tend to react in similar fashion, because they have similar electron configuration. If I need one more electron to fill that row, to fill that orbital, wouldn't that make sense that bromine is typically 1 minus? If 3p5, it took one electron to fill that 3p orbital. Chlorine wanted to be 1 minus. Fluorine wanted to be 1 minus because they all were a 1 electron shy of a filled orbital. Calcium, which had 4s2, it would take 2 electrons to empty out that 4s orbital. Calcium wanted to be 2 plus. If I looked at magnesium, magnesium would have been 3s2. It wanted to be 2 plus. Beryllium would be 2s2, 2 plus. There's a reason behind why the table's set up like it is, because we want to be able to have all these properties be the same. Okay, so here's the answer worked out. Just for you guys' sake, in case you can't read on the board, it's here. It'll always be here. Now, as you go through the test, we will not always use those diagram sheets. We might just use the periodic table. But if you have a periodic table in front of you, you can modify it so that you can utilize this, and it's really, really easy. When you come in here next time, take a look at the periodic table on the wall. I've already pre-modified it in order to better understand that. You'll see here that above the 1a and 2a orbitals, I wrote S. Above the 3a/13, 4a/14, 5a, 6a, 7a, I wrote P. Those are the p orbitals. Above the transition metals, I wrote D, and above the lanthanide and actinides, I wrote in F. That essentially, in here, these elements are filling in their various orbitals at a time. Each row will designate the highest energy orbital that is filled. So 2s, row 2 will be filling the 2s and 2p. Now, the only thing to note is because we go 3s, 3p, 3d, this is a 3d orbital. But we don't access it to row 4 because that's when the transition metals start showing up. So you'll notice that in the periodic table over here, I've written row -1. So as you're working your way across, you'll have 4s, then you jump to 3d, back up to 4p. When you're working on row 5, it's going to be 5s, 4d, 5p. Row 6, 6s, 5d, 6p. The lanthanides and actinides are, the row F is available on the 4th row, but it's not used until the 6th row. It's available on the 4th, but it's not available to the 6th. So it's row -2. So you'll notice that we have 6s, 4f, 5d, 6p. So I've written row -1 for the transitions and row -2 for the lanthanides. But we can work our way across. So if I said, what is carbon? I would say 1s, 1s2. 2s2, 2p2. This is where carbon is located in the table. Silicon, finish out 2p6, 3s2, 3p2, right here in the table. I can work my way across this table, filling it in as I go. Da 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 da. Bromine, bump up 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 4p5. That's where bromine appears. So you can use this table as you work your way across to find what is the electron configuration of any element. Now there's a few exceptions for the D's and the F's, which is going to be responsible for the weird charges of some of the transition metals. We will not worry about learning or memorizing the exceptions. There might be something in the homework, but I'm not going to call you on, oh, there's a weird exception where it's like 4s1, 3d5. I'm not going to call you on that. So we will end on this slide. I will briefly just look at this, and then we'll begin next week on next class on the next slide. Now, the most important thing here is the valence electrons, and we'll get to this a little bit more next chapter, but these electron configurations will tell us how they react, and it's going to be how we predict the trends. But the reactivity is controlled by the outermost shell, the valence level. The outermost shell is the valence level, and those electrons are the valence electrons. The idea being, if this is like a shield, you have multiple different shields, multiple different barriers here. You have to breach the first barrier before you can get to the innermost defenses, that nucleus. So you have to go through the valence electrons before you can react with anything else. So all the reactions are going to happen at that valence level. Any of the inner layer of electrons are going to be called the core electrons, and they're going to not react, which is why it doesn't really matter that chlorine has 17 electrons and bromine has 35 electrons, because chlorine has 7 valence electrons and bromine has 7 valence electrons. So they react the same because they have the same number of valence. For all main group elements, the number of valence is equal to the total number of s and p electrons. Also going to be the same as the group number, which is how we could easily predict the charge of atoms. All electrons, okay. That's where we're going to end. But next class, we're going to talk about how we can actually condense that electron configuration down into a shorter version that just shows us the valence electrons. So I don't have to go 1s2, 2s2, 2p6, like speaking like I'm an auctioneer. That's where we end. Have a nice day, and I will see you in lab.